Welcome into the next video in my series on essential skill number 1 for AP Chemistry, dimensional analysis and mole conversions. In my last video, I covered solution stoichiometry, a particular type of stoichiometry involving aqueous solutions and molarity. And in this video, I'm going to cover a very common application and sort of lab procedure involving solution stoichiometry, which are titrations. So a titration is often performed with an acid and a base, although it doesn't necessarily have to be. It can theoretically be performed as long as we have two aqueous solutions that are reacting, but most commonly with an acid and a base. And we're slowly adding one of the reactants to the other. So we have one reactant in this Erlenmeyer flask at the bottom, which we call the analyte. And then we have another reactant in the burette that's above it, and that reactant is called the titrant. So the titrant is added to the analyte. So this little lever at the bottom of the burette is called a stopcock, and that can open and close. And when it opens, it allows the liquid to fall through into the analyte. And so basically what you would do is you would fill the burette, you would close the stopcock to make sure none of the liquid is going out. You would fill it at least part way with your titrant. Record, it doesn't necessarily matter how high you fill it, as long as you have enough, but however high you fill it, you want to record that initial volume reading because the burette has volume readings like a graduated cylinder would. And then you're going to slowly open the stopcock and allow the titrant to flow into the analyte and react with the analyte. And when you think that the titration is over, which we'll talk about on the next slide, when that might be, you would go ahead and close the stopcock, stop letting out any more liquid, and then read what your final volume is on the burette. And the difference between those obviously is going to tell you what volume of the titrant that you added to the analyte. And usually we're trying to determine some property of the analyte here. Maybe the molarity of it is very common, something like that. So in a titration, one property of a titration is what we call the equivalence point. This is very important. So the equivalence point is the point in the titration where we've added just the right enough amount of the titrant to fully react with the analyte. Because if we think about it, initially, when we add titrant to analyte, first of all, they're going to react, but that's only going to use up a little bit of the analyte because we only added a little bit of the titrant. And as we add more and more of the titrant, it's going to react with more and more of the analyte. Okay, so we keep adding titrant, we keep using up analyte. Well, eventually the analyte's going to run out. We've added enough titrant, there's no analyte left. And then if we kept adding titrant beyond that point, which we could, there would be nothing for the titrant to react with. So we would just be adding excess titrant. And then we would have titrant in excess in the flask. Okay, so before the equivalence point, we still have excess analyte. Okay, it hasn't all been used up. Beyond the equivalence point, we have excess titrant in the flask. Because we are adding more of it, there's no analyte left for it to react with. So the equivalence point is that perfect point where we've added just enough titrant to react with all of the analyte, but we haven't added any excess titrant beyond that point yet. And this is generally the key point that we're going to use in titrations to do stoichiometry calculations. Now the end point is usually meant to approximate the equivalence point, but by definition, they're not necessarily the same thing. So the endpoint is usually where we observe a color change, and the color change is due to the use of what's called an indicator. Okay, and we pick our indicator, which is oftentimes for these acid-base reactions, phenolphthalein, okay, although there are some other ones depending on the specific acid and base that are used, but this is the kind of the most common one. But you pick your indicator so that it will change colors as close to the equivalence point as possible. Okay, and the reason these acid-base indicators change color is based on the pH. Okay, But by definition, the point where the color changes is not necessarily the equivalence point. By definition, it's the end point. But if the experiment is sort of designed properly, that gives us a good approximation of the equivalence point as well. So oftentimes we will make the assumption that the equivalence point is the point where we first observe the color change. All right, so let's look at a titration calculation example. And this really is just a solution stoichiometry problem. There's not really anything special that we're going to do in terms of the calculation as opposed to a regular solution stoichiometry problem. It's just important that you understand some of kind of the terminology and the context of what's going on here in a titration. Okay, so we have 25 milliliters of an HCl solution of unknown concentration, and it's titrated with 0.1 molar barium hydroxide. So that's our titrant. The HCl is our analyte. So let's first write out the chemical reaction that's occurring, as we would do first in any stoichiometry problem. So we have HCl plus BaOH2. This is an acid-base reaction, a neutralization reaction. Okay, but we can kind of treat it like a double replacement reaction. So the products, you're going to combine H plus with OH minus. That's going to give you water, which is almost always a product of a neutralization reaction. And then your other ions, barium and chlorine, are going to give you BaCl2, since barium has a +2 charge, chlorine has a -1 charge from the periodic table. So 2 chlorines, got to put a 2 here and a 2 there to balance it. Okay, and then here's our molarity equation. Okay, and we know about the barium hydroxide. We know both the molarity of that and the volume, 20 milliliters. The HCl, we don't know the molarity, but we know the volume is 25 milliliters. So we're always going to start with the one that we know more information about. Okay, we know two things about these, the molarity and the milliliters, which we can convert to liters. And so we can find the moles, either using this equation or using, I'm going to do it using dimensional analysis. So we have 20 milliliters of barium hydroxide, which I'm just going to write that, divided that by 1,000 to convert to liters. So that's going to be 0.02 liters of barium hydroxide. You could show that step if you want. You don't necessarily have to. Just dividing by 1,000. That's a unit conversion, metric unit conversion. And then, again, either way we do it. If you use this equation, you could just use this equation and say molarity times liters is going to give us the moles. I'm going to do it using dimensional analysis, but it's the same calculation. It's 0.1 moles of barium hydroxide per liter. That's what 0.1 molar means. The liters cancel. I get my moles of barium hydroxide. This is how many moles of barium hydroxide we added from the burette into the flask. And then our equation tells us that for every 1 mole of barium hydroxide that we are adding, it is reacting with 2 moles of HCl. So if we do this calculation, that is going to give us how many moles of HCl were in the flask and were reacted with by the barium hydroxide that was added. So that's 0.004 moles of HCl. And keep in mind that this only tells us the amount of HCl that was in the flask because we're at the equivalence point. Okay? If we were at some other point in the titration, this would just tell us how many moles of HCl have been reacted with at that point in the titration. Okay? But at the equivalence point, that's the point, as I mentioned earlier in the first part of the video, where we have added enough of the barium hydroxide to react with all of the HCl. Okay? So when we've added this 20 milliliters, all of the HCl that we started with has been used up, but also we haven't added any excess. Okay, so if we added 40 milliliters of barium hydroxide, well, not all of that would have been used up. So if we did a calculation with that, we wouldn't get the right answer. So the equivalence point is the perfect point where we've added just the right amount of the titrant to fully react with the analyte, but not too much. So that's the point we want to do for point we want to use for these sort of stoichiometry calculations. And then it's asking for the concentration, which by that it means molarity unless otherwise specified. Molarity is a type of concentration, but it's by far the most common type that we use in chemistry. So for the most part, you can use concentration and molarity interchangeably unless otherwise specified. So to find the molarity, we take these moles of HCl, and then we already know that we had 25 milliliters of it. So the molarity of HCl, which remember that's what this notation means with the brackets, is 0.004 moles over 25 milliliters. Again, divide that by 1,000, 0.025 liters, and you get 0.16 molar is the concentration of HCl.